Okay, so let's make a start. So today it's great to have Ananth Shankar to talk to us about Tori in positive characteristics.
Thanks very much for having me. So everything that I talk about is joint work in progress with Anup Dixit, Phil Engel, and Ruofan Jiang. So it's going to be fairly gentle talk. Please feel free to ask questions at any point. So let me start off with a statement that's well known, especially to people over here in characteristic 0. So let, for instance, x contained in C star to the n be an algebraic subvariety. And let's say irreducible. And let's also assume that it contains the identity point, just for simplicity, because you can always translate, such that x intersected with C star to the n of the torsion points, namely roots of unity, is dense. Then it's well known that x has to be a subtorus. And of course, it goes by Mann and Mumford.
Torus kind of. Isn't that before?
Their conjecture also holds. Now, theorem also has been made in setting of abelian varieties.
Yeah, that's.
Okay.
I think we are distinguishing.
I think Reno gave a proof of this. I don't know if it's the first proof or not, but
No, that's abelian variety.
abelian varieties. So who was the
The
first?
other case goes back even to Gordon from Topshin Gordon, I would say.
Okay. So yeah, so this is a very classical theorem. It's been known to talk like. And well, one thing that's striking is that it's just patently false in characteristic P.
So saying the same, the closure of any bunch of torus points of torsion points is a subtorus.
That's exactly right. You have to be really careful because it could be, first of all, there could be irreducible components. So each irreducible component should be subtorus, but that's not quite true either. Because you could take a subtorus and you could translate it by torsion point. So it's a torsion coset.
Okay.
But then once I say
it is a torsion coset. For some of the other theorems, there could be cosets not by torsion in the Lang-GM proof.
and that's why I want it to contain the identity, just to get rid of. Yeah. But absolutely, another way of phrasing it is that you take a bunch of torsion points, take Zariski closure, every irreducible component will be a torsion coset. And as Peter says, there are other settings where the sort of state we end up getting is a non-torsion coset. And in fact, as we'll see, things like this will show up in the Cassie setting. Okay, but now instead of working over the complex numbers, what if you were to work over a field of characteristic P? Let's just take K equal to FP bar. The point is, every element of this is a torsion point. So it's just patently false to expect the Zariski closure of a bunch of torsion points to be a subtorus. So here's a more broad question one can ask. Well, the question that one can ask, instead of asking for, so somehow something that goes wrong is that every FE bar valued point of this is torsion.
And you would still be wrong over like some gigantic field or?
Well, I think that's the thing. So that's a bit, all your torsion points are defined as FP bar. So it's not like you get any new torsion points over. So you've got a denser torsion points, you're like automatically going to be defined over FP bar. So yeah, that might have been one way to correct the problem, but that sadly doesn't work. Now, another question that one can ask over here is if your subvariety contains a dense set of torsion cosets, then you ask for it to be a subtorus, or like a torsion coset itself or something. Now, despite every point being a subtorus, despite every point being a torsion point, every subvariety is not a coset. Because it just isn't. So you could try to ask the question of what happens if you were to replace torsion point by subtorus or torsion coset. Now you could do that over here as well, but you end up getting the same question because every torsion coset has a Zalski dense set of torsion points in its own right. But what happens in Cat P? So that's the theorem we'll talk about. Joined with Anup Dixit, Phil Engel, Ruofan Jiang. And in fact, let me just take the most general version. Maybe one moral of the story is that torsion point, it doesn't really matter whether your point is a torsion point or not. It's just, instead of working with torsion cosets, just work with arbitrary cosets. Here's a theorem. So let's just take k equals k bar for simplicity. Let x contained in gm to the n be an irreducible subvariety. Such that X contains a Zalski dense set of positive dimensional cosets. Cosets of subtori. So then you can't expect your X to still be a subtorus because let me just give you an example. Let's look at GM cubed. And I'm going to write GM cubed as GM cross GM squared. And now I'm going to take a curve, any curve inside GM squared, and I'm going to look at this cross GM. Well, this has a dense set of cosets because for every point of C, you can look at that point cross GM. And the theorem essentially is that that's all you're allowed to be. Then up to a GLNZ change of coordinates. We can write n equals a plus b such that x is of the form, let's say, x1 cross, or let's say gm to the a cross x1 So up to chaining coordinates, you can write down your torus as a product where your x also splits as a product, where one factor is the whole torus and the other factor is going to be something. And visibly, if everything is defined over FP bar, an x of this sort clearly does contain a dense set of torsion cosets, positive dimensional torsion cosets. Okay? So eventually, when I talk about proofs, I will sketch a proof of this theorem. But before this, let me state some other results that we obtained, which aren't directly related to this, but are sort of in the same orbit of some sort of transcendence / formal geometry in positive characteristic.
You have something in the abelian variety?
Great. So yes, if you replace your GM by E and GM to the N by E to the N, everything goes through. I expect something very similar should go through in the case of general abelian varieties. I haven't thought it through yet, but things should work.
Is this functional transcendence? I mean, in characteristic 0, this would just be consequence of X Shen 1.
Absolutely. That's right. But we of course don't have that.
It's different, yeah.
It's, yeah, exactly. Yeah. Yeah, we haven't checked the details of what happens in the case of abelian varieties. But everything definitely works for powers of an elliptic curve. Okay. Now, there is a question of trying to characterize subvarieties that happen to be torii or cosets. And this doesn't say very much about that question. So here are some expectations that we have. I'm sorry?
Characterize in what terms?
So if you were to give me a subvariety of GM to the N, then if it's a CAD 0,
yeah, you can write
you can ask whether it's a subtorus or not just by asking for whether it has a dense set of torrent points or not. Now, how do you do that in CAD P? If you were to give me a subvariety of GM to the N in CAD P, is there like a way to test whether it's a subtorus? Containing a dense set of positive dimensional cosets is not a test, but we expect the following conjecture to hold, let's say. So just take let's say that this is reducible, geometrically reducible, and we'll say everything is defined over F cubed. Now, suppose X is not contained in any subtorus, then, well, so here's something that you can do. You can look at, if you want to exploit the group structure in some way, what you can do is you can look at the FQ points of X for every Q, let Q become bigger and bigger and bigger, and maybe try to work in the group structure in GMTN to ask a question or to say something. And one question that you can ask is, how many points of X defined over FQ have exact order Q minus 1? So look at the number of points in, let's say, FQ prime, such that the order of X is Q prime minus 1. Now let's divide this by the total number of points, which is approximately Q prime to the dim X. And let's take the limit as you range over all, like over all extensions containing F cubed. Do you have a question?
Yes.
Oh, okay. Because of the Shimura thing?
Oh, cool. It seems kind of crazy. I want to see what you say.
Oh, okay, great. Great. All right. Then we expect that this should be 1 minus 1 over p to the n. divided by zeta of n.
Wait, what's
What's P?
what's P? Yeah. P is the characteristic.
P is the characteristic. Yes. Okay, so why this quantity, you might ask? Well, here's sort of why. Replace x by gm to the n and take this ratio. This is exactly the quantity you get. It's not hard to check. This because you don't have any points of order p. Otherwise, it would be the whole zeta value. So we sort of expect that if you were to take an x that's not contained inside a subtorus, then you expect that the number of points, that the proportion of primitive root as it were contains should be the same as the whole torus. Now, under using Chebotarev, we can show this as an upper bound. Now we have an example where this is an equality. Maybe let me call this proposition. So look at GM, the n cross GM.
Sorry, what is the conjecture?
The conjecture is that you look at this ratio as
always go to that if you're not contained. Yeah, so
exactly, and if you're contained in a torus, then your n just becomes smaller, and your n just will be replaced by smaller number.
So okay.
So yeah, so now here's why I sort of phrase this in terms of testing whether a subvariety is a torus or not. Take a subvariety, calculate this ratio. The zeta value that you get, is it going to be this n or is it going to be smaller n? If it's this n, then yeah, the zeta value you get, if with the dimension of your variety, then it's a subtorus. That's what we expect.
Sorry, can you say that again?
Sorry.
So like,
Sure.
given this conjecture, if you could prove it, you
if
could
you
test
could.
whether you contain a subtorus,
No, whether you are a subtorus or not.
whether you are a subtorus or not. Why are you
Yes.
testing whether you are a subtorus or not?
It's a question. Why? Meaning, why would one want to? Why does this?
Growth rate.
Yeah, doesn't this test whether you're contained in a subtorus?
Well, okay. So you look at the growth rate. If the growth rate happens to equal the dimension, if this n equals the dimension of x, then yes.
But
Yeah.
it doesn't like dovetail with that, it's a different direction.
Completely different.
Okay.
The thing is, because this doesn't say anything about whether you're subtorus or
Yeah,
not.
okay.
And
I understand.
so look at GMVN plus GMVN, and let's say that x1 through xn is a set of coordinates for the first thing, y1 dot yn is a set of coordinates for the second thing, and define x to be the vanishing locus of x1 y1 plus x2 y2 plus xn yn equal to 0. Then this x, for this x, this limit does exist and it does equal zeta to n. Equals what it should equal. I should say this is like this example was very much inspired by an example in a paper of Jacob and mine where we worked with not a product of tori but a product of modular curves, and in Cat P we come up with a divisor inside a product of modular curves which intersects every isogeny class, which should not happen in Cat 0. Okay. Now, let me say a little bit more about this. So I didn't write this down, but I said that if you were to, I said that you could.
Unconditionally, what do you know? You know, you're the upper bound. What can you state? What you can prove?
The upper bound.
Yeah.
So unconditionally, we can prove the upper bound. Let me say a few words where that comes from. So it's a Chebotarev type argument, and the reason why we get the and the reason we're able to use the Chebotarev type of argument is that what we would need to use the Chebotarev type argument is that if you have an X sitting inside Gn to the n, this X has to have big monodromy in some sense. So let me state, okay, so let's look at the following setup. You've got X, let's always assume it contains identity, irreducible, so on and so forth. Mapping to Gn to the n. So let's look at the L part of the fundamental group. That's going to map to the L part of the fundamental group of this. Let's call this ZL. This is ZL to the N. Now, then okay. Now, what's the image going to be? It's going to be some sublattice. If you're working in characteristic 0, you don't have to work with Ital pi 1. You can actually just work with the honest fundamental group. And if you work with the honest fundamental group, you have Z to the N. And it's easy to show that if you're not full rank, then you're contained in a subtorus. Because you just project away from that part, and then you get a map from your X to like a one-dimensional torus. And if it has trivial, imagine if the image of the fundamental group is trivial, then it has to contract to a point. So you have to be contained inside a subtorus. Now over here, you have irrational subspaces because there's like no natural Z structure over here. There's no topological fundamental group. Everything is like, a priori, there's nothing that rules out the image of the fundamental group from being contained inside an irrational hyperplane. So our theorem is that that can't happen. And sorry, I should say, if that were to happen, then any sort of Chebotarev trick one might want to use to come up with upper bounds for like an arbitrary variety would fail. Because the fundamental group is smaller, when you like take various covers of GMV and pull back to X, you start getting things that are reducible covers, not irreducible covers. So for any Chebotarev type of argument to work, and in fact for this to even be true, you want a statement that says that this image is going to be full rank if your X is not contained in subtorus. In other words, if your image is not full rank, then you are contained in subtorus. And this question is not obvious simply because you have sub-linear spaces which are not rational, which are irrational. But of course, the theorem is a posteriori that can't happen. If you contain inside an irrational hyperplane, you contain inside a Q hyperplane. That's theorem. Suppose X not contained in any subtorus. Then image of pi 1 has full rank.
So can you get this geometrically by looking at like the X of the curve, for example?
Yes.
Can you look at it as like Picnard or something? It's maybe the
That's a good question. So okay, you could ask the same question if you replace Gn to the n by for example a curve or like by Nabelian variety.
Sorry, G to the by Nabelian variety?
By Nabelian variety, and then just work with Jacobians, work with H1 being the Tate module, use Tate's conjectures and so forth. I'm not sure whether that's going to work over here.
Okay.
Yeah. I don't think so.
Did you explain how you proved that?
No, I haven't yet. I just told Jacob why.
You talk very fast, so I don't even know when you proved something.
No, please feel free to ask me to repeat anything. I was just shooting Jacob down.
Preparing me to be shot down.
That's right. So again, maybe there's some argument. Maybe there's some argument, but I prefer ours in any case. And there's another theorem that we also prove. So, okay, fine, maybe a full rank, but maybe you're like a sublattice with of like finite index, and that finite number is bigger than 1. And a priori, that could happen for every prime, that could happen for infinitely many primes L. And that'll also mess things up over here. If it would happen for finitely many primes L, then you can at least you can always like lift your map from X to GM to the end to like a finite cover, and then you'll be surjective. Okay. So let me just put a small asterisk over here because I might want to assume like maximal monodromy, not just full rank. But yeah, but what we prove is that for L big enough, this is actually surjective, and so you have an adelic finite index theorem. Okay. So there's also a p-adic companion to this, which some might allow me to think of as a log-ax Lindeman theorem. So let x inside GM to the n is as always. Now, well, okay, so now ideally what you want to do is you want to somehow work at the Lie algebra identity, you want to work with the exponential map, none of this makes sense in perfect characteristic. What you can do is you can, however, complete at the identity, then you get a formal group, and as it turns out, that formal group has way more subgroups than GM has algebraic subgroups. In fact, the set of formal subgroups of the completion of GM to the n at the identity is like a ZP object. It's parameterized by ZP data, whereas subtorii of GM to the n, algebraic subtorii of GM to the n are parameterized by Z data, not ZP data. You've just got more. So take this setup now, take the formal completion of X at the identity, and of course you can look at the formal completion of the ambient space at the identity. Now suppose you happen to be contained inside some formal subgroup, and let's say you're properly contained. Then, so one way of sort of thinking about this is you have C to the n mapping to C star to the n. Now let's take some let's say hyperplane, which is not necessarily defined by rational, which is not necessarily a rational hyperplane, not necessarily defined over rational numbers. Now suppose some irreducible component of happen to be contained inside V. Then the conclusion in Cat 0, and this is what I think followed from Ax Lindeman, or log Ax Lindeman, would be that X is contained inside an algebraic torus. So this setup should be thought of as analogous to this, and we prove the same result. And surprisingly enough, the proof of this is very similar to our proof of this result. So I sort of think of this and this as aladic and p-adic avatars of each other. All right, so I think that's it for the statement of results. If there's no questions, let me start talking about how we prove the theorem that I just helpfully erased. Namely the geometric Monodromy theorem. Jacob, you thought,
Yeah, this last question, this theorem you have.
yes.
Do you have it in other setups as well, like e to the n? Or
Yes, so it'll definitely hold for e to the n.
You think
This should hold. Okay, so this should hold for A. This I think should hold for A.
this actually be true. I'm wondering if your proof should go through.
Almost certainly.
Okay.
Almost certainly. Yes. And okay, so one reason why I prefer proof to your candidate proof in this case is that I don't think you can make that work over here.
You come back and explain your proof of that.
Yeah.
Okay, so
Okay,
hopefully.
do that. Because you haven't erased that yet. So. The only assumptions X not contained in a subtorus.
Yes.
We're watching.
And do you have, sorry, do you have the reverse as well, the axial Lindeman, which would be?
That's easy.
That's easier?
Yes.
Okay, yeah, that's what I figured.
So the axial Lindeman would be that if you have a formal subgroup contained inside X, then you have an actual subgroup contained inside X, but then you just exert closure.
And that just works.
That just works.
Okay.
So I'm sorry, I'm actually going to first prove the Monodromy thing and then. Okay, so proof of the Monodromy thing sort of goes via understanding jets. So let's look at the jet space at the identity, but of depth R of Gm to the n. Now, sitting inside here is what we call the space of rational jets. I'm going to define what these are in a sec. And they're indexed by algebraic co-characters of our torus. So given any algebraic co-character, I'm going to give you a jet.
And for you, a jet is like a map from the germ of a curve.
For me, a jet is a map from spec k epsilon mod epsilon to the R to there where the reduced point goes to the identity. Great. Okay, so now here's my definition of J lambda R1. So I'm going to think of this. Okay, so for me, Gm to the n is K1, T1 inverse, T2, T2 inverse, Tn, Tn inverse. So look at K epsilon mod epsilon to the R, and let's map. Yes.
Is this the one on the top in the middle? Which theorem is this?
Sorry, this is the theorem that I've erased. The theorem that says that if you've got a dense set of positive dimensional cosets, then you're a product something crosses subtorus.
Isn't this theorem right there?
Yeah.
Oh yeah, I did not erase it. I did not erase it. It's this theorem. Yeah, it's this theorem. I thought it didn't erase it.
now.
Okay, so let's see. Look at K epsilon mod epsilon to the R and just look at the map. That sends Q to 1 plus epsilon. So this is like, given a one-dimensional torus, this is just like a tautological jet you can define. And any co-character is a map, is a group homomorphism from here to spec k ti plus minus. All right. And just compose. So just compose, given co-character, you get this jet. I'm calling that a rational jet. Okay, that's it. Now, here's why rational. Rational because if you were to work in Cat 0, then these are fit exactly by Q linear lines inside the Lie algebra. So these jets are fit by Q linear lines in the Lie algebra. So Q rational, that's exactly where that comes from. Now, here's a miracle. In Cat 0, there's lots and lots of rational jets. There's infinitely many of them. In Cat P, it all collapses down to a finite set. And that's because if you've got two co-characters that are congruent mod a big enough power of P, then they give you the same jets. They give you the same rational jets. Let me write that up. Write that up here. So let's say that let's take some power of P that's bigger than the depth of your jet. Then if you have two co-characters that are congruent mod P to the S, then this jet, the two jets are the same. And the proof is a straightforward computation. Boils down to saying that if you raise 1 plus epsilon to something like P to the S, then you get 1. Okay? And that's it. Then that tells you that the number of rational jets, if you fix your depth R, then the number of rational jets is going to be finite. Of course, as R becomes bigger, you have more and more different rational jets, but if you fix R, there's just finitely many of these. Now, just like there's a notion of left invariant and therefore right invariant vector fields, there's also a notion of left invariant and right invariant jets. Your group acts on the jet spaces. You can just take a jet at a point, translate it, smear it around the whole jet space of your GMPN, and what you end up getting.
Sorry, what does this mean? X star GM to the N.
Oh, sorry. So this is the co-character lattice of GM to the N. Okay, this is just.
Oh, it's not nothing to do with X.
I'm sorry, it's unfortunate notation. You're right. Nothing to do with X. This is just the co-character lattice.
Oh, X is just about jets in a torus.
Nothing to do with X. Just about jets in a torus.
Okay.
Jets in a torus is positive characteristic.
Uh-huh.
So I'm just saying that if you've got two co-characters that are like congruent mod big enough power of P, then the jets they induce are going to be the same. And then that just gives you finiteness of these types of jets. And that finiteness is going to be key. All right, so now define rat R to be GM to the n invariant jets whose fibers at the identity lie over here. Okay. And this is just going to be, as a variety, as a scheme, this is just going to be a finite union of copies of Gn to the n, each of which maps down by like an isomorphism to Gn to the n. And like no two different things meet, they like, you just get a finite totally split étale cover of Gn to the n. Let me just say one other thing. If you take this space, take a jet over here.
I mean, just because it's pushed around by GM to the end.
Exactly.
Okay.
Exactly. Like nothing deep going on over here. Now, if you were to say, yeah, if you were to take a point that's not identity, and if you were to look at what jets you see, the jets you see are precisely jets that are realized by one-dimensional cosets passing through that point. That's just because they like translated by the group operation. Okay. Fine. So now let's look at. Okay. So now let's go to the proof of the theorem. You have the jet space of X mapping inside the jet space of GM. And that also contains the space of rational jets. So define XR to be this jet space intersected with the space of rational jets. All right, so this is a closed subvariety, this is a closed subvariety, the section is going to be closed. This maps down to X. Now, by assumption, X contains a Zariski dense set of positive dimensional tori, and therefore, the image is going to contain a Zariski dense subset. At every point through X where you have a positive dimensional subvariety, you contain a rational jet. So the image of XR is closed because this map downstairs is a finite map, and also dense in X. So going from a dense set of points where you have a rational jet, you get that every point you have a rational jet. This is true for every R. So what we have is that for every R and every X in X, there is a rational K jet in X, rational R jet through the point little x. Now, all of this does not give you that you have a torus passing through X, because what could happen is that for every point you have some co-character. In fact, for every point in every R, you have a co-character. Now, as your R becomes bigger and bigger and bigger, it's not a priori true that the same co-character is going to work. You've got a sequence of co-characters, but the point is that your sequence of co-characters will be more and more and more congruent, more bigger and bigger powers of P. And so your sequence of co-characters will converge not an X star of Z, but an X star of Z tensor ZP. Now, that is a space of formal co-characters. Now, whatever that sequence of co-characters limits to, that's going to give you an embedding of a formal torus inside your Gn to the n, and therefore your X will contain that formal torus. Yes?
You have these jets. How come you're not, it just feels like, could you just be not using jets, but only kind of like things that are closely related to one parameter subgroups? Because you're composing with these things anyway, I mean.
So you're right. I mean, like, I am looking at jets which are.
Oh, those
But exactly
are,
right.
those are the only ones you're really.
Exactly. These are the only one primary subgroup. Like you don't really. Okay.
So that's what you're really looking at, is like little pieces of subgroups.
Exactly right. That's exactly right. And the point is, like, as you look at bigger pieces, you don't convert to an actual subgroup, you convert to a formal subgroup.
Okay, and now we're back to the other theorem.
Now we're back to the other theorem. That's right. But the easy version of the other theorem. But then by taking that, okay, so just translate back to fidelity and okay, whatever. So not a coset, but an actual formal subgroup.
Yeah, that's what you meant. Before it was inside of a formal torus. Now it's a formal torus inside of X.
Exactly. And that's the easy situation because now just take the Zalski closure. It's going to be contained inside X. It's going to be a group.
Okay.
So you win.
Wait, I'm sorry, before you erase that statement,
Yes.
could you explain the limit one more time? Because I think there's something that's confusing me about it. Could you just state what the limit is again?
Okay, so if I may, you're like very right to be confused. So here's what I mean. I want the limit to have the property that every field is eventually going to be contained. Every finite field will eventually be contained there.
Okay.
And let's say that I order by inclusion.
Yeah. But so what confuses me is I don't see why this limit shouldn't just be one, right? Like if you say you proceed in the tower of like extension of degree 2 or something, like isn't the numerator just the set of points defined over the top field that isn't defined over any subfield?
No, it's not true. It's not true. So F2 to the
F2 squared, right? Aren't in FQ.
like you've got fewer primitive roots than elements that lie in that field.
I say I'm sorry, yeah.
Like yeah, it's a bound, but
Ananth, can I ask you about the thing you just proved?
yes,
I don't know if I can't remember the dates. I don't know if you mentioned Grushovsky's work on Mann and Mumford.
I did not.
Cool. So how does it relate to yours? Because it seems like neither of you quite proved the other's result, but maybe I'm confused.
no. So I think it's quite different.
Maybe somebody, let's see.
I think Grushovsky says that if you just look at actual torsion points and he considers field heuristic P.
So first of all, Grushovsky doesn't work with Tori, he works with the abelian varieties. What he proved, he defined a subvariety of an abelian variety to be special if your subvariety is defined over FP bar, or if it's a sub-abelian variety.
Okay.
And what he says is that if you have a dense set of torsion points, then you're special. Now for Tori, I don't think this result says very much because I think his main thrust is
You're saying his method won't work for Tori.
I think even the statement is vacuous.
Yeah.
Because his main thrust is for abelian varieties not defined over FP bar, but defined over a bigger field.
Sure.
Tori, you can't do that.
Sure. I see. But okay, so for abelian varieties where your stuff, like for e to the n, where your stuff should also work.
Yes.
Then you can relay.
Then you can.
So
relate them.
I think I think his result is again going to be vacuous because he cares about torsion points not defined over FP bar.
Yeah.
But if your E is defined over FP bar, oh sorry, so you're saying that one of my E is not defined over FP bar.
Yeah, that's right.
No, that's a great question.
Then his result's not vacuous. Look at e to the n is not defined over FP bar. But I don't think it's in the same direction as yours. You're right.
No. This is a very good question. Okay, so for us, we don't care about whether your coset is torsion or not. Oh, that's a good question. We should think about whether we can show that. Whether we can recover his result because he already proves that if you've got a dense set of torsion points, then you're a subvariety, you're subabelian. That's a good question. We should think about it.
So can we?
Yes.
Sure, in a hurry, but I'm just trying to figure out how this happened. We just had a bunch of torsion points, and then we ended up with a whole bunch of jets.
Sorry, so we have no torsion points. We have
in this thing, right?
positive dimensional.
No, sorry, they're not torsion points, they're these subvarieties.
Exactly, they're like subgroups in fact.
Okay, so we have loads of jets there.
Exactly. And that's exactly that. Those are the jets that give us our rational jets.
Okay, I get it. I mean, at least conservation of idea.
Absolutely. Yeah, ours is an entirely geometric statement. Like we can't say anything for zero dimensional special things.
Mhm.
That's a great. Okay, so take Zalski closures, your formal thing becomes algebraic. And so what you end up getting is that through.
Wait, is it supposed to be order equal? I'm so sorry to ask the same question.
Yeah, no, not at all.
Order of x equals q prime minus 1. Isn't that just saying that it?
It's a primitive. Well, if your n was 1, like if you were a point in Gn, then I'm saying it's a primitive root.
Right.
A generator for the multiplicative root.
Okay. I'm sorry.
I don't know, you're right. Like generators are not defined over smaller fields, but you have elements that are not generators that are also not
I'm
defined.
sorry. Yes. Okay. I understand. Yes. Sorry.
Okay. Now, how do you conclude? You want to say that it's the same subtorus, and for that, you don't work over FP bar, you base it on FP bar to some big enough field, which has like uncountably many points or whatever. All of this didn't use FP bar. We could be working through points defined over any field. Then you get that for a Zalski tensor of points, it's going to be the same torus, projecting it from that torus. Okay. So let me just conclude. Because I can now talk about the other one. All right. Let me do the theoretic one if that's okay. It's like very similar argument. You need a different argument. You need slightly different argument for like the open image thing, but theoretical thing is more or less the same. All right, so here's the argument for log Ananth Lindeman. Let's say that I have GM cross GM cross GM. Let's say that I've got a C mapping over here. And I'm going to assume that C is contained in a two-dimensional formal torus. So now doing things affine locally, let's say that the coordinates on these are Z1, Z2, Z3. Let's say the coordinate ring of C is R. And let's say Z1 maps to R1, Z2 maps to R2, Z3 maps to R3. Okay, fine.
You're proving the full rank or Logarithmic Lindeman? Logarithmic Lindeman right now.
I'm proving Logarithmic Lindeman and very similar argument goes through for full rank, except we need to like work with covers instead of directly doing this, but it's a similar argument. Okay. Fine. So I'm going to let's assume that the image of C formally at the identity is contained in the locus Z1 to the alpha, Z2 to the beta equals Z3. This is a formal locus in which the alpha and beta are numbers in ZP, and there's a formal locus which contains ZP, not Z. you take R completed at the identity, then SPF R maps to this formal locus. Now, what does that mean? What that means is, if you were to look at the completion at the identity of R, then you have that R1 to the alpha times R2 to the beta equals R3. Let's pick a sequence of integers an and bn that periodically converge to alpha and beta. What you end up getting is that R1 to the an times R2 to the bn times some quantity, which will be R1 times R2 times to some power, but raised to a big peak power is going to equal R3. Now, in other words, I want to say that R1 to the an times R2 to the bn divided by R3 is a big power, not in R, not in the function field, but in the local function field. But now here's the point. Your global function field is sort of perfectly closed inside your local function field. Here's what I mean. You take an element in your global function field. If it admits a p-th root in your local function field, it already has to admit a p-th root in the global function field. So all these are elements in the global function field. They become p to the nth powers in the local function field. So therefore, they were already p to the nth powers over here. Okay, so we're upgrading from something local to something global. Okay, so now how do we use this? Well, let's now what I want to do is I want to use this to now come up with a Q relation between A and B. Once I come up with a Q relation between alpha and beta, not A and B, alpha and beta, then we win. Now here's the thing, pick some point in C, but the compactification of C, where perhaps one of these functions vanish. These functions are not going to vanish on C, they're going to be invertible on C, but unless they're constants, they have to have zeros or poles somewhere. If all the functions are constant, then the map is a constant. So see when let V1 be VP of R1, V2 be VP of R2, V3 be VP of R3. And I can always assume that there is some point in the compactification, maybe some boundary point of C, where not all of these are zero. So then what you end up getting is you get that AN V1 plus BN V2 is congruent to V3 mod P to the N. Well, okay, but then alpha, like you take the limit, you get alpha V1 plus beta V2 equals V3. So you actually have a Q linear relation amongst these numbers in ZP that gives you what you want, because then you can find an algebraic subtorus, one-dimensional contained inside this formal subtorus, mod out by that, and then use regular action. All right, thanks very much. Let me stop this.
What did you mean when you said something about monodromy?
What does it help?
Right, so there was also the aladic statement. And I wanted to say that if you have a C mapping here, and if it's not contained in any subtorus, I wanted to say that its fundamental group has to be big. Now, an argument similar to this works, except maybe it's a bit more involved. If your thing dropped rank, but say it was like a priori irrational something containing it, you can still approximate it by rational hyperplanes, and using that, you can cook up a bunch of finite covers so that this lifts there, just by the Itard lifting property. Now, once this lifts over here, you get a similar, you get like similar types of relations, except instead of p powers, they'll be lth powers. And everything's algebraic because I'm not working, I wouldn't be working over something formal, I'd be working over something algebraic. So you get a bunch of relations with these functions, except there's going to be, except like some sort of ratio will be an nth power. And then you again just pick some point where something has to vanish and you construct a rational relation.
The trick is like the points at infinity, kind of the order vanishing there gives you your Q structure or something.
Exactly. That's exactly right.
But the problem is only if it had.
Other questions? Okay, let's thank Ananth.